So last time we started an example that's going to have a chemical heat source. So what we have is an insulated tube. That tube is full of spherical particles. And the reason why we have spherical particles is that they increase the surface area for any type of reaction you'd like to have. So basically in this middle point, which is of length L, we have a reaction zone that has spheres that have catalyst surfaces. So this is essentially a problem with the porous medium, right? So we know that like when we are solving these problems, we need to know, typically in order to solve, we need to know what the velocity field is in order to actually couple with heat transport, especially if we're going to solve anything analytically. And we're going to pretend we know that here, but we're not going to go into the details of the flow in between spheres. We're actually going to work with the average Darcy solution. Okay? So in that sense, when I actually look at the thermal conductivity, then my thermal conductivity has to be also the one that we're going to take into account is the averaged one or the effective one, okay, of this porous medium. So there's just something to think ahead. And that's fine. That's how we also measure things. So that's all just fine. So what we have is a one-dimensional problem. That part is simple. So it's an average problem. It has a velocity Vz. This is my Darcy velocity, which I denote as V0, and it's assumed constant. And my temperature that I'm solving for is temperature just of this Z variable. So we know something about the reaction source term. While it's happening on the surfaces, it is actually kind of volumetric addition of heat inside of this volume. Now you will have two ways to add anything to the volume. It could come from the boundaries. Okay, that would in this case not be applicable because I actually have this averaged volume. So whatever boundaries of the spheres I have, I don't have access to them one by one to actually put some boundary conditions in there. Okay, so I'm treating this as a volumetric term. Okay, but if my heat source, for instance, was this boundary, which is right now insulated wall, then I actually could treat it using boundary conditions. So there are different ways to actually deal with sources. Okay? But in this case, the volumetric term is more applicable. And it's something that is measured. So this is some function. T1 is the temperature that I have here. And T0 is some sort of far field, or it's a fitting parameter for this equation, T0, and SC1 as well. So those are the two parameters that I have, and T1 is actually the temperature that I measure from the outside. So this is, I just pretend I know this. Okay, this is this function or this source term is known. So what I do then to balance is I can imagine my little tube, even though this is a 1D problem, so I could have just drawn a line. Okay, but volumetrically I do have some surface, some area of the tube times the combined heat transport vector or flux vector that comes in on this side minus what comes out at the other side. The area is the same. And then this is the volumetric term. So this is my volume times the heat per volume. Okay? And that has to be equal to 0 in steady state. So I divide by my volume and take the limit when delta Z goes to 0, and that gives me a deceptively simple differential equation that says partial Ez partial Z is equal to SC. So let's take off from here. Okay. What is my Ez by the time I open a new one? Am I not recording? So what is my EZ? One over 2? I heard that. Blah, not needed. Good. Plus rho H. So what is this part of the? This is the convected part. So this is what flows in. Well, flows in plus. There's enthalpy here, not just internal energy. So there's part of the work built in there as well. So enthalpy is internal energy U plus PV. And it's a heat, measures heat content of the medium. Plus tau. So in this case, the Z component would be simply tau ZZVZ. Okay. So this is the Z component of tau dot V. And plus QZ, or Z component of Q. Cool. So here, this tau ZZ, it has to have some sort of partial VZ, partial Z in there as partial derivative, and minus 2 mu. Since that is 0, my VZ is Darcy velocity that is assumed constant, so this is going to disappear. And my QZ, this is where I'm going to assume that it's some effective in Z direction, of course, because Z direction and other directions are not the same thing in this medium because it's insulated. I don't actually care about cross direction, but they're different. So some average Z direction. Okay. And again, this is my effective. We take effective K into account since this is a porous medium. Now, if I take the partial derivative with respect to Z of this, my part that has enthalpy in there is not just going to disappear this time. So I can't get around that. So I actually have to go and calculate what it is. So let's actually introduce a formula that is going to help us with that. So how do we calculate? So we need to calculate this. I'm not gonna derive everything, but I'm just gonna sketch the idea of how this is done. So my enthalpy, it's a state variable in thermodynamics, so it depends on pressure and temperature. Just as a reminder, so it's internal energy plus PV. The way I measure it is I keep pressure constant, and then it's equivalent to, when I do work, it's equivalent to the all the work that gets transformed into heat in that system while keeping pressure constant. As usual, I measure things by measuring differences. So by chain rule, if I'm about to measure anything, the only thing I can measure is changes in energy, never just the energy itself. So by chain rule, this is it is the partial derivative with respect to T while keeping pressure constant, dt, plus partial derivative with respect to pressure while keeping temperature constant, dP. This, by definition, is the heat capacity. And this, I'm just going to use a ready-to-go formula without proving. So this is the thermodynamic equilibrium formulas. Minus T dV dt while keeping pressure constant dP. So this is specific volume or 1 over rho. Again, this is just, I'm just using the formula for this part without proving it. So the way I actually get the formula for enthalpy is by integrating this from some reference state. And that reference state is P0, T0. So it's from T0 to T, Cp dt, plus from P0 to P, V minus T dV dt and again I'm going to go to ready to go. So this is equal to 0 for ideal gas and 1 over rho P minus P0 for fluids of constant density. So basically for fluids of constant density, this second term disappears. This one is constant and then it's easy to integrate. And I'm not going to care about any other fluids. Constant density. We had in the entire course, there's that one example with the compressible gas at the very beginning. That's about it. Okay, we're not dealing with compressibility. And it's plenty complicated with just assuming constant density. We don't need more complications. All right. So this is essentially the formula I'm going to use. So in this case, I'm going to have, so this integral is also simple. Let me just then, for fluids of constant density, basically I have Cp T minus T0 plus 1 over rho P minus P0. Okay. Using here. Okay, so now I have all of the elements. What I'm actually solving is that dEz dZ is equal to Sc, right? So may as well solving. So now actually let's get what dEz dZ is about on the next page. So my dEz dZ is equal to d dZ of 1/2 rho Vz squared plus, now I can actually write what my rho h is. So it's, our expression was for h minus h0, so this is rho h0, the reference state, plus rho Cp t minus t0, plus rho times 1 over rho, that's 1 minus p0, Vz. And minus that effective the heat conduction term, all of that is equal to Sc. Since my derivative of Vz is equal to 0, by chain rule this is going to go to 0. This is a constant, so this is going to go to 0 once I take a derivative. Okay. This one, so the one that is not constant or depends on z is t, and then here p, and this term here. So these three terms survive, and what we have is rho Cp dt dz plus dp dz dz and the second order derivative of t in the heat transport term. So I have pressure and temperature and velocity all bundled together. Plus this SC could well, if I'm modeling it, it's going to be something linear, but or we can make it linear or linearize it, but it could add some complexity. Yes?
What about the
Vz is constant. So the second term in the chain rule, sorry, I just kind of shoved that under the carpet. So his point was, well, there's the term for here that I took the derivative of the first term times Vz, and then this times dVz dz, which is 0. Right? So I just skipped writing that. Skip writing that and skip saying anything about it. So, all right. And then the second term. So this already, it just has 3 terms, but it's not an easy thing to do analytically. So first assumption that we're going to make is that our pressure changes are relatively small and that our Vz is relatively small. So when multiplied together is even smaller and can be ignored as a first order solution. Okay, so we got rid of the pressure one. Let me see what else can I get rid of. I still have dt dz and then k effective d squared t dz squared. Now this is something that, and since I know the velocity term, right, that's fine. So this I treat as known. This is something that if I had the software, I could go and solve for. But I could also still simplify. I could say, okay, well, which term is actually dominant? Because we have a convective term, stuff that is that has Vz in there, and this is my heat transport due to the temperature differences only. And whenever you have two types of transport, you should consider, well, which one is dominant, because one of them might be small enough that it simply can be ignored, so there's no need to go into solving. And this is the actual situation we're going to look into. So we're going to basically assume, so assumption number 2 is that Reynolds number is relatively large. And by that, I mean it's larger than 200. So in that case, convection is dominant. And the regular heat transport that is just due to the temperature differences simply doesn't have time to catch up. So whatever differences it might bring to the table are too small to be acknowledged. This is also measured by that Peclet number, which is Reynolds times Prandtl number is large. So in that case, we have rho Cp dt dz Vz is equal to Sc. Yes?
That's a question. So we use the Prandtl number to know which if the momentum of heat transfer is dominant, right?
Mm-hmm.
The Reynolds is for convection and convection.
So there's also convection of what is simply brought into the medium versus the standard velocity differences in between the layers. So this kind of bundles all together into one. Okay, so Prandtl number exists even if I don't think about stuff that is simply brought into the medium. That's the momentum within. It's like that binning. We bin all of the contributions separately, right? So it's kind of all encompassing everything due to the velocity. Okay, so this is actually then relatively simple, assuming that my Sc is simple. It's Sc divided by rho Cp V0. So this is some Sc1 f of T minus T0 over T, normalized temperature. So this problem can be normalized, and it often is. We use theta as T minus T0 divided by T1 minus T0. So that is dimensionless temperature. And my Z is Z divided by L. Or Z, this is uppercase C. I'm just going to call it Z tilde because there's no way in my handwriting to tell the difference between the two. So then ddz is one over L dc. And then you can basically go in and replace this. So this will, with a little bit of algebra, give you something like this. and f of theta and my n is, I'm going to squeeze it in here, LSC1 divided by T1 minus T0, rho Cp, a bunch of stuff I know. Mm-hmm.
Why is that d over dz bar? Is it just dz bar?
Oh, yes. I was looking at this and it just, so ddz would be ddz bar times dz bar dz, right? I would use a chain rule. So if I was, yes? V0, yeah, we called it Vz before, just to keep that z in there, but now it's a constant V0. In formulas, I wanted a reminder that it's a z direction velocity, that's all. The point is, n is something that I know. So the way I would proceed about this is I can do separation of variables. D theta over f of theta is equal to n dz bar, right? And then I would integrate. I need to know f of theta for that. In the simplest case, it's just theta. So simplest cases are always linear, and if you can do away with linear, then do it. Don't complicate your life, it's already complicated. Okay. So if linear works, no need to question it, okay? Very fine, move on. Otherwise, it's a known function, so I can still do separation of variables and solve it. So, and I need boundary conditions, okay? And simplest boundary conditions would be given at this z bar, or normalized length is 0 and normalized length is 1. Now, I can't always know what the temperature is going to be at the end, z equals L, because I might possibly have an uncontrollable reaction going on in there. So that's something that I don't necessarily always know, but I can impose it that it's finite. Okay. All right. So various types of solutions can be looked at in here. So need boundary conditions and form of f to solve. Now, if I actually don't ignore this term, then I need, so we're not going to go into solving that, but basically I do think that one can actually solve analytically. Even the second order one, it's not necessarily simple, but I need the form of this K effective, okay? So K effective is something that is fitted to the size of the particles, the heat capacity of the system, and the velocity that is going through, okay? So I'm assuming I have that term. There are some formulas that can help with evaluating it, but overall I need, and it's possibly something that depends on Vz. In which case this can get complicated, right? So I would then get like a different solution, and then I have to deal with the second order equation. And possibly numerical software is the way to go. Okay? BC's boundary conditions. I need boundary conditions and form of f to solve this. Right? But once I get that, it's a separation of variables because I can divide by f of theta and multiply by dz. Okay. You should solve problems 10.6 and 10.7 on your own. And we are going to go through (10.8). So this is laminar flow of a viscous constant density fluid in a cylindrical tube, but I'm going to have heat coming in from the boundaries in radial direction and flow in z direction. All right, this is something that is very common in petroleum engineering. Okay. I might need to heat my tubes to actually get the oil flowing. Okay. So now, are those pipelines with laminar flow in there? Maybe, maybe not. Depends on the size of the pipe. But in this case, I'm just going to assume laminar flow. Okay. Just to show you an example problem. So this is going to be laminar flow of a viscous constant density fluid in a cylindrical tube with constant radial heat influx through the wall. Again, conceptually, problem is very important because even if you don't have heat source, you might have great heat losses depending on how your insulation works or if you have insulation, right? So if your pipe is made of highly conductive material and you don't have any insulation and the outside of the pipe is much cooler than the inside, then you might get great heat losses. And even if you don't calculate what the heat transport is, well, what it basically can happen is that you can start, you're changing the temperature inside the pipe, and as you're changing the temperature inside the pipe, anything from phase transition to asphaltene precipitation to hydrate formation could actually happen. So this type of problem is really important to consider. So we assume the following. The fluid has constant properties for the time that we're solving the problem. Again, which might or might not be correct for the situation. If the temperature is considerably changing, so does viscosity, right? So we do have to think about that, even if we initially solve the simpler problem. So we can decouple the problem. So our step one is find the velocity profile first. Well, actually, we did that already in the previous chapter. And then use velocity to find temperature profile. So the first one is momentum balance, second one is the energy balance. Now here we're going to keep the properties constant, but if that's not the case in some future case you're solving, then you would update the transport coefficients according to the new temperature, right? And update your velocity profile accordingly, and then keep going, right? So step by step. This decoupling strategy would still work, or that's the only one we can do. So this is so let me just draw the situation. This is my length L, radius R. The direction, and then what I have is in radial direction I have heat flux. So my boundary conditions are then my QR at R is equal to R. It's given, and it's minus Q0, where Q0 is a positive value, meaning I'm flowing counter R direction, right? Opposite the coordinate. So Q0 assumed positive. There's some heating coil around tube. And my temperature at L is equal to 0 is some known temperature. Okay, so my velocity profile I know from before. It's pressure for mu L, 1 minus R squared over R squared. So it's my parabolic profile, and I'm just going to refer to this as Vz maximum times 1 minus for simplified writing. So this much is simple. Now my heat transfer it is fun because it's going in both z direction and r direction, right? So if I look at my shell balance, I'm going to draw myself a shell, my egg shell. Good news is my career does not depend on nice drawing. And there's this thing called computers visualizing things for you. So there's stuff going on in radial direction, right? There's going in, and this is my radial direction in and out, right? And then for z direction, I have this top, boundary flux in, and also flux out. I don't see the bottom surface. So my vector E is 1/2 rho v squared plus rho enthalpy plus tau dot v plus q. So I got to balance this vector components going in through radial and z directions. Yes?
Why do you want drawing the arrows outside if the flux energy going inside to I mean, you are drawing the arrows outside.
Outside?
But, yeah. But if I understand the problem,
Oh, this is just, I'm drawing them in the coordinate directions. They're going to figure themselves out to be negative. Right. Yes, the R probably direction. But like this shell balance, we have in minus out, right? And what I mean by in terms. So I got to go in coordinate directions to develop a partial differential equation. Partial differential equation doesn't know that my boundary condition is negative. Partial differential equation, it kind of obeys the coordinate system. All right, so basically I'm just going to write down the balance. So my R component is ER. So this ER is going to be negative if it needs to be, right? Minus ER. And this is multiplied by area at R is equal to R, and then area at R is equal to R plus delta R. So I collected everything going in and out through surfaces orthogonal to R direction. Plus, and then I have EZ evaluated at Z times, just calling this surfaces AZ and AR for now, Z plus delta Z, AZ plus delta Z. So in and out through Z surfaces orthogonal to Z direction. And plus I have work done by external forces. Okay? In this case, it's gravity. And then volume. AR, AZ delta Z, right?
Why is there the gravity? Do you that is flowing downward?
Hmm?
Your fin is flowing downward. The long way is vertical.
Right. So it's G is downward and our Z is pointing downward too. So this is really GZ, which is G. So this would be a vector, right? Force or external forcing vector dot velocity, but both are in Z direction. So this is work done by gravity, external force. And I'm just gonna remind myself that AR is 2PR delta Z. AR plus delta R is 2PR plus delta R delta Z. And my AZ is difference between the outside, outside and inner disk areas. And at this, well, I'm just gonna approximate this. So this is approximately P to R delta R. So I'm ignoring delta R squared term. Okay. This is actually a very good time to stop. So we continue deriving this on Wednesday. Okay. Keep warm.